What if something is tiny, I mean really tiny, like a human sperm cell, could completely flip our understanding of physics on its head?
It sounds pretty wild, doesn't it? Like something out of science fiction.
Exactly. But that's precisely what we're exploring in this deep dive.
Mm-hmm.
Today, our mission is really to unpack how the seemingly effortless way sperm move through thick fluids actually challenges classical physics.
And in doing that, it provides some pretty compelling evidence for this revolutionary idea called motion theory.
Yeah, our insights today come from some fascinating excerpts titled Sperm Don't Break Physics, They Prove Motion Theory.
Should be interesting.
So yeah, prepare to maybe see the fundamental nature of reality in a profoundly new light.
Let's jump right into the central paradox here.
Okay.
Scientists observed human sperm moving with surprising ease through highly viscous fluids, stuff that should be really hard to move through.
Right, and the puzzle is that according to classical physics, Newton's third law of motion specifically, this just shouldn't happen so efficiently. We all remember Newton's third law, right? Every action
Has an equal and opposite reaction, yeah.
Yeah.
It's baked into how we understand the world, billiard balls hitting each other, a rocket taking off.
perfectly sensible for those big macroscopic scales. That symmetry, that push and pull, it makes total sense there.
But when you zoom way down, like down to the microscopic level.
Like a single sperm cell swimming.
Exactly. Swimming through something, you said, like molasses. Well, that classic action-reaction principle seems to just break down.
Yeah, classical physics predicts a huge amount of resistance, drag. But the sperm just keeps going. Pretty efficiently, too. It's a real head-scratcher.
It absolutely is. And the scientists studying this, they were really grappling with it. They started using terms like odd elasticity and non-reciprocal interactions.
Which sounds like science speak for we don't quite get this.
Pretty much.
Yeah.
They were essentially acknowledging that their existing classical frameworks just couldn't fully explain what they were seeing.
Which, raises a huge question. If our basic laws don't quite fit the picture, what's really going on down there?
And that's the cue for motion theory.
Right. This is where motion theory steps in, offering this really profound reframe of how we understand reality itself. This isn't just tweaking things. It's like putting on totally different glasses.
It really is a different lens. Motion theory proposes something pretty radical. It suggests that particles, forces, all those things we think of as fundamental building blocks, even physical laws, they aren't fundamental in themselves.
Okay, wait. If they're not fundamental, what are they?
They're seen as, and this is the key phrase, simplified descriptions of structured synchronization loops resolving across gradients.
Whoa. Okay. Structured synchronization loops resolving across gradients. Let's break that down a bit.
Yeah, it's a mouthful. Think of it less like tiny billiard balls bouncing off each other,
Okay.
and more like maybe ripples or waves interacting and organizing themselves. These loops are self-sustaining patterns of motion, like rhythms.
Rhythms? Okay. And resolving across gradients. What does that part mean?
That just means these patterns, these loops, respond to differences in their environment, differences in energy, density, whatever. That gradient helps direct or shape the pattern.
So it's like everything is part of a larger coordinated dance. Is that a fair analogy?
That's actually a great way to put it, a coordinated dance. Not just independent things pushing, but interconnected patterns unfolding.
All right. So if reality is built on these synchronized loops, these patterns, how does that change something as basic as force? We think of force as a push or a pull.
Right. Well, in motion theory, force itself gets redefined. It's seen as motion resistance.
Motion resistance, not a push or pull.
Exactly. It's not some separate thing acting on an object. It's more like a property emerging from the interaction of these motion patterns.
So Newton's laws, are they wrong then?
Not wrong, no, just incomplete. They become simplified labels for structured motion behaviors observed at macroscopic scales.
Okay, so they work for our everyday world because all those tiny, complex loops average out into something that looks like simple action-reaction.
Precisely. They're excellent approximations for the big picture we usually deal with.
That's a big shift.
Yeah, okay.
Okay, so let's bring it back to the sperm. If force is resistance, how does motion theory explain its super efficient swimming? That's the mystery we started with.
Right, back to our little swimmers. At these tiny scales, motion theory says the key isn't traditional forces, it's this structured loop synchronization.
The loops again?
The loops again. What looks like it's defying Newton is really just structured motion loops operating without the need for external reaction forces.
So the tail isn't paddling against the fluid in the way we normally think.
Exactly. Think of the sperm tail less like an oar pushing water back and more like it's propagating these rhythmic motion loops internally. It's generating its own wave, its own rhythm within itself.
Like an internal engine driving a specific pattern.
Kind of, yeah. A perfectly choreographed internal dance, you could say. Each bit of the tail follows the rhythm, setting up the next movement smoothly. This lets it maintain forward momentum without needing that strong, equal and opposite pushback from the fluid.
Because it's not really reacting to the fluid in the classical sense, it's generating its own sustained motion pattern.
You've got it. It's more proactive than reactive.
Okay, that helps visualize it.
Yeah.
So let's revisit those terms the scientists used, odd elasticity and non-reciprocal interactions. How does motion theory reinterpret those?
Good question. Odd elasticity, from the motion theory perspective, is basically a mislabeling of rhythmic synchronization.
So it's not stretchy like a rubber band.
No, the flagella's motion isn't elastic deformation in that sense. It's described as a structured rhythm with internal phase encoding. The tail actively maintains this synchronized internal loop. Each phase of the rhythm flows into the next, creating propulsion without needing those external reaction forces.
It's all about the internal rhythm, not pushback.
Right. And non-reciprocal interactions. That term actually fits perfectly with motion theory.
How so?
Motion theory predicts exactly this kind of thing. It calls it feedback-rich structured synchronization. Each movement phase of the tail doesn't just happen. It directly sets up the conditions for the next phase in the sequence. It's a continuous feedback loop.
Ah, so it's non-reciprocal because the tail's action influences the next action within the tail itself, not necessarily getting an equal reaction from the fluid.
Precisely. This self-sustaining feedback loop structure allows motion continuity without symmetrical reaction forces. That's why they seem to glide through thick fluids so easily, they bypass the need for that classical interaction.
Wow. It really turns the whole thing inside out. It's humbling, isn't it, that something so small could point toward such a different view of physics.
It definitely is.
And the implications, then? They must stretch way beyond just sperm cells, right? If this theory holds water, what else does it explain?
Oh, absolutely. The authors suggest, and it makes sense within the theory, that this has huge implications for understanding collective motion and self-assembling systems.
Like flocks of birds or schools of fish, or even how molecules build structures.
Exactly that kind of thing. Think about a murmuration of starlings, those incredible fluid shapes they make, or how complex molecules might spontaneously form specific structures.
Okay.
Motion theory suggests these aren't driven by classical forces like tiny magnets pulling each other around necessarily.
So how do they happen then?
The idea is that these collective behaviors emerge naturally as nested loops align their rhythmic phases. Individual loops sync up, creating larger, coordinated, synchronized structures.
So the flocking pattern isn't every bird following a leader, but more like their individual flight patterns synchronizing into a bigger pattern.
That's the concept. It's an emergent property of synchronized motion. Classical physics sometimes struggles to explain that kind of emergence gracefully, but for motion theory, it's a natural outcome.
So the big takeaway is that sperm aren't breaking physics at all.
Not at all. Instead, you could say they expose the inadequacies of classical interpretations at microscopic scale.
Right. Newton's laws aren't wrong for our world, our scale.
They're just incomplete simplifications of structured synchronization patterns.
Right.
They capture the averaged out effect, but not the underlying dance.
Okay, so motion theory seems to resolve these puzzles by putting structured motion, this idea of rhythm and synchronization, right at the heart of reality. And the sperm, swinging so effortlessly, isn't some weird exception. It's actually a really clear, visible example confirming that these structured motion loops are fundamental drivers.
A perfect case study, almost. The scientists being surprised and inventing new terms just underscores that gap between the classical view and this deeper, motion-based reality.
So wrapping up, the sperm haven't broken physics.
No, they've revealed its true structured motion foundation. And if you take that leap, it suggests that maybe countless other things we find puzzling in physics or biology might suddenly make more sense if we look at them through this lens of structured motion and synchronization.
Which leaves us with a pretty big thought, doesn't it? What other phenomena out there? Maybe the flutter of a butterfly's wings, maybe, I don't know, the way galaxies form over cosmic time.
Could they also be examples?
Yeah. Could they just be more complex, more elegant examples of these structured synchronization loops playing out? Are there everyday things we see that seem simple, but are actually hiding these deeper truths about reality, just like our tiny, intrepid sperm.
It certainly makes you look at the world a little differently.